All right. So as you already know, there is a frequency domain technique. This is the chapter 2, right? Frequency domain. So frequency domain. This is chapter 2, and that technique is also called classical technique. Okay. Now we'll be doing, instead of frequency, we are doing time now, right? So frequency is now time. So in time domain, we'll solve the similar problem again. So that technique is now called so-called modern technique. Okay. So mainly there are two techniques. One we call classical, the other one modern, right? So and this technique is also called state space approach. State space approach. Okay. So we'll talk about state variables there. So we find some variables that can describe the system completely. Okay. We'll find some variables, or I would say set of variables, or set of variables, okay, that can describe the system completely. Those variables are called state variables. That could be current, it could be voltage, that kind of thing. So these variables, which can describe the system completely, are called state variables. And the space is called state space, right? So state space approach can be applied to wider class of systems, unlike the classical approach. Okay, in the classical approach, in the modern approach, we can solve more problem as compared to the classical approach. So even though we can do that, but in this chapter, we'll limit our discussion to the similar system that we did in the chapter 2, because if you go beyond that, that will be out of scope of this course. Okay, so even though we can do it, we don't do it. So we'll do the same problem using different approach, which is modern approach or state space approach, right? Now, the benefit, the advantage is that it can be applied wider class of system. When I say it can be applied, is I meant the state space approach, right? State space approach can be applied to wider class of system, but the downside is that it is not as intuitive as the classical approach. It is not as intuitive as the classical approach, because the designer has to engage in several calculations before the physical interpretation of the model is apparent. Whereas in the classical approach, a few calculation or graphical presentation of data rapidly is the physical interpretation. So that's the downside. Okay. Let's see how this state space approach work. Suppose you have, in the case of classical approach, if you remember, we had a differential equation, right? Okay, let's say the order of differential equation is nth order. Mainly we did second order, right? Mainly with the second order differential equation. That's what we did. Okay. So now in this approach, in the state space approach, what we do is we change our second order differential equation in general nth order. Okay. In general nth order differential equation into n number of first order differential equation. in general, okay? So if you take n equals 2, then in other words, the second order differential equation, if you start with second order differential equation, then you will have two first order differential equation, okay? So step one, I would say step one, write nth order. In our case, for example, second order, right? So if you have second order differential equation, then change it to the second order goes, you have two first order differential equation. One looks like this and the other looks like this. Okay, so what is there? On the left hand side, you have the derivative of x1. Okay, derivative of x1. By the way, this x1 is called state variable. Okay, this can be current. I don't know, di over, d, let me call it q, dq over dt. Your q is now x1. Okay, that's what I meant. From the second order differential equation, we have two first order differential equation. So one has dx1 over dt. Remember, this is the x1 and x2. By the way, these are called state variables, okay? x1 and x2 are called state variables. Then on the right hand side, what you have is the coefficient times x1, state variable here, then coefficient, state variable here. So this is called linear combination of state variables, okay? So when you write this way, you call it linear combination of state variables. Linear combination of state variables. That's what you say. Not only that, you also have the source. For instance, if you have a circuit like this, what is the source here? Source is V. Okay, so you have source also. So I don't know, I1 could be, x1 could be Q, x2 could be I, right? Your source could be V because this is the source of your system, right? So the conclusion, the two first order differential equation can be written in terms of state variables x1 and x2 and the source. Similarly, other one, x2 also can be written in terms of state variables x1 and x2 and source. This is what the first order differential equation look like. So from second order, we have two first order. Then your goal is to figure out, let's say, I don't know, let's say the voltage between here. This is our goal. This is your goal. So VL, you need to figure out VL, right? Then your output equation, so which is VL, right? This is your Y is VL, equal to, again, the linear combination of x1 and x2. So you have here the linear combination x1 and x2, you have linear combination x1 and x2. Here also you have linear combination x1 and x2. And also you have the source term there. So output also can be written in terms of x1, x2, and the source. Okay. So let me put this inside the box. x1, x2 are the state variables. Now question is x1, x2, is the choice of x1, x2, suppose you are doing this problem, we are solving this problem, right? So is the choice of x1, x2 is unique? The answer is no, okay? Choice of state variable for a given system is not unique. You could have maybe, I don't know, this could be, I and Q, or it could be, BC and Q, it could be I and VC, it could be I and Q, it could be VC and Q, it could be in any set, okay? This is just an example. So some of them may be forbidden. Maybe this is not the valid choice, right? We'll figure that out. I'm just trying to say that the choice is not unique. Okay. So which one is valid, which one is not valid, we'll figure that out. Okay, the choice is not unique. So, but there is a requirement. It's not unique, but there is a requirement for choosing state variables. Is that they should be linearly independent of each other. So what do I mean by linearly independent? Suppose x1 and x2 are state variables. Let me say there are 3 state variables. We are talking about third order differential equation, right? Then you have 3 state variables, x1, x2, and x3. If you have 3 state variables, then somehow if you can write x3 as a linear combination of x1 and x2 like this, then in that case x3, in that case your x3 is not linearly independent. In other words, it's linearly dependent. Okay, x3 is linearly dependent on x1 and x2. Okay, there should be. So again, what is the conclusion? The choice of state variable is not unique, but one thing you have to keep in mind that they shouldn't be linearly dependent, or they should be linearly independent while we choose them. So far so good. Right question here? So far so good.
Yes, sir.
Okay, now, so how do you know which variables are linearly independent or not, right? So suppose you chose 2 variables, you know, let me say I and I don't know, I, Q and I. Are these linearly independent? How do you know? That's the question, right? There is a rule of thumb, okay? I'll call it rule of thumb. The rule of thumb is that a quantity and its derivative are linearly independent. That's the rule. So is this true here? Can you write one as a derivative of other? I equals dq over dt. That's why this q and I, they are linearly independent. Does it make sense? So you can choose, this is the valid choice. Q and I is the valid choice for the state variables. Okay. Now, so we have to have the minimum number of state variables. You cannot have less than minimum. Otherwise, you cannot describe your system. That's why I call it minimum. You have to have at least, suppose you have second order differential equation. If you have second order differential equation, you have to have at least 2 state variables. So 2 is the minimum. So the minimum number of state variable is equal to order of differential equation. If you have second order, you have 2 state variables, the minimum. If you have third degree differential equation, you have to have minimum of 3 state variables. If you have fourth degree differential equation, you have to have minimum of 4 state variables.
I have a question.
Please.
I find myself confused a lot about the difference between order and degree.
Oh.
Do you mind explaining? Or is it in this case, is it interchangeable when talking about the number of state variables? Okay, no.
So let me so d square y dx dy over dx plus y equals 0. dy over dx squared plus y equals 0. What is the degree of differential equation here? What is the order? What is the order here? Order is 2. What is the order here? Order 1. How about degree here? Degree 2. Oops. Yeah, degree 2. Does it make sense?
Yeah, so you're saying like the degree is kind of like if a term is like has an exponent?
Yeah.
Okay.
This is degree. This is order. No, other way around.
It's the other way, right? So, sir,
Right.
is it basically 3 degrees for the other one, the one above?
Yeah, I didn't get that. Would you mind repeating it?
Yeah. So for the above equation that you've written, would it be 3 degrees for that?
No, this is just first degree.
Oh, okay.
Okay. Yeah. So that's the thing. So second derivative means you have second order. Okay, that's the thing. Does it make sense now?
Okay, so yeah, so it's order that's related to if a term has an exponent.
Order if it is not exponent. Did I understand your question clearly?
All right, so I guess I'm just trying to understand the difference still. So order, like so you say the bottom one, the order is the second order, and is that because the dy
No,
dx is
no, bottom one is order 1.
okay? I thought you said you had switched around the terms.
Oh, did I? Sorry.
Okay, all right. That's why I guess I'm. All right, my bad.
I'm sorry. So I did write properly, but maybe I said something else. Jen, did I lose you? Are you there?
Sorry, I'm trying to write.
Oh,
So
okay, that's okay. That's okay.
I can't like click the unmute button quick enough.
Okay, that's fine. I'm just one. So does it make sense now?
I think it helps. So yeah, so the degree then on that bottom equation is due to the fact that that term is squared, correct?
Exactly.
And so the first equation would be first degree.
Yes.
Also? Okay.
Yeah.
All right. Thank you.
All right. Okay, so where I was. So yeah, so minimum number of state variable is equal to the order of differential equation. So that's the rule. Now, in most cases, so one way is to see the order of differential equation and figure out the minimum number of state variables, right? That's the method 1. This is method 1. Another method is to determine the number of state variables by counting the number of independent energy storage elements. You count number of independent energy storage element. Okay, I'll talk about that in the next slide. Okay, what is energy storage element? I'll talk about it. For now, I'll just count those elements. If those kind of elements, suppose there are 2 energy storage element, then I will have 2 state variables. If you have 1 energy storage element, then I'll have 1 state variable. Does it make sense? This is how you figure out number of state variables. Okay, so this is the minimum. So for the second order, oops, I know why you are confused. Now I have been seeing degree again. For the second order differential equation. Yeah. So thank you for the correction. I now I realize I have been saying that. Okay. So we get points for that, Jane. Don't forget that. So now, so we have minimum number is minimum number is equal to order, right? Order of equation. But however, you know, many times if you write the equation by including additional state variable, not only minimum, add, you know, maybe one more, okay? Instead of having minimum number, add one more or two more. If you do that, that makes your life easy in writing state equation. But the thing is, you have to pay the price for that. Well, how do you pay the price? The solution is more difficult then. All right, let's do one problem here. Hopefully this will. All right, so here our goal is to find the state space representation. State space representation of this electrical circuit. If the output is the voltage across the inductor, let's say this is your output. This is what you are interested in. You are interested in BL. Okay. So now how do you represent this system in state space representation? Okay. So first of all, what is your, you have to first do the first order differential equation. Sorry, second order differential equation. So how does the second order differential equation look like? In this case, help me. So how do you write the second order difference? So first of all, let me begin with the loop equation, right? So what is the loop equation or Kirchhoff's voltage law? So there is only one loop. So this is VT. What is the voltage drop here? If current is I, then IT R, then what is the voltage here? Help me. Anybody can help me, please? So what is the voltage here? The voltage here is, voltage drop here is Q over C, right? So what is Q? Q is 1 over I dt. So we can write, you know, you can simply write this, okay? So voltage is Q over C. Emery, you have a question for me?
Oh, sorry. Nope. I think I'm good.
So then what is the loop equation? So if we start from here to here, then what do you get? From here to here, you're going uphill, right? So VT. Uphill meaning plus. From here to here, you are going downhill. ITR. From here to here, you're going downhill. LDI over DT. And from here to here, you are going downhill, which is 1 over C I dt equals 0, right? So take these guys on the right hand side, then you get VT equals this. L di by dt Ri and this guy here. So then now I need the second order, right? I need the second order. So how do you change it to second order now? Will you please help me? So this is definitely first order, right? So this is di by dt here. So how do you change it to second order? So we know I equals dq over dt. The derivative of q is I. So if you plug in here, then what do you get? So L d over dt. I is again dq over dt plus r, what is your I? dq over dt plus 1 over c. You can simply call it q. So it means L second derivative of q, that's what it is. Then r dq over dt, that's what it is. Then plus 1 over cq equals bt, right? That's your bt. So we got the second order differential equation. We got the second order differential equation. Step 1 is done. Step 1 is second order differential equation. Now, step 2. Step 2 is, so write 2 second order differential equations. Because of this order here, because our order is 2, so we have to write 2 first order now. Two first order differential equation. Okay. All right. So how do you write this one? Let's choose a variable called I equals dq over dq dt, right? So can you rewrite this? Actually, in practice, we are going back again. Okay. Let's call I equals dq over dt. This is one equation, right? See, this is second. This is first order differential equation, right? dq over dt equals I. This is first order differential equation. Now, with the help of this equation, can you rewrite this guy? Actually, you are going back here again. See? So L di over dt, then Ri, then you have 1 over C, this guy is Q, right? So 1 over Q over C equals Vt. So can you rewrite this guy? Can you rewrite this guy as this? Look at here. So divide both everything by L. What happens if we divide everything by L? L divide by L divided by L, right? So if you do that, what do you get? So this L and L cancel out. Then you have di over dt on the left. Then Ri over L, right? You get Ri over L here, Ri over L. So minus, right? Minus Ri over L. Then what is this guy here? Q over CL minus, right? Minus Q over CL. Then you have Vt over L. So Vt over L. Now if you look at this, you have 2 first order differential equations. You realize that? So what are they? This is the one of them, and this is the other one. Now the question is, now do you have the, what is your state variable now? Figure out the state variable. Can you figure out the state variable? Are the state variable? Is this Q and I are the state variable? Yes, no, maybe, I don't know.
Yeah, that seems to make sense.
Because there is state variable because one is the derivative of other, right? So if one is the derivative of other, so Q, I'm claiming that Q and I, because I have 2 first order equation. One is derivative for Q, the other one is derivative on I. So that's why my claim is that this Q and this I, they are state variable. Because this is true, right? If dq by dt equals I, so this, in that case, Q and I are linearly independent. That's why they could be state variables. So meaning Q and I could be state variable. That makes sense. Okay.
Wait, quick question. You're saying state variable, does that mean interchangeable?
Interchangeable. No. State variable mean the variable that are required to describe the system completely. So if you know Q and I, if you know Q and I of the system, right? Suppose I give you Q and I, then you can figure out voltage here, you can figure out voltage here, you can figure out voltage here, everything. That's what I'm trying to say.
Okay.
You solve the problem.
Okay.
So state variables are those variables which completely describe the system. You can find,
okay. Thank you.
you can find anything you want. Okay. All right. So now these are my two first order differential equation, right? From the previous slide. Okay. So this is the one, this is the other one. We have two first order differential equation. Now step 3, what I do is I want to write the state space representation of the system now. What I meant by that is I want to write in the vector form. Okay, vector. Or I would say matrix, okay, rather. Because sometimes, or matrix, yeah, that's fine, vector, actually vector form. All right, vector form. So vector is also matrix, right? Yeah. So here, now your differential equation, remember these two guys, this can be written as, these two guys can be written in this form. So what is this? Where, see the thing, the bold, right? Bold letters here. X is bold, A is bold, X dot, by the way, this is X dot is bold, A is bold, X is bold, and B is bold, right? But this U is not bold. Okay. So this is vector, bold, this is vector. A, this is matrix. X, this is vector. And B, this is vector. And this is not vector, this is scalar. Okay. So now my claim is these two guys can be combined in this form. Okay, let's see. So for that, what I do is, I'll do this. What I do here is this. So my claim is that if I write this way, I'll go backward, okay? Then you'll understand. Once you do a couple of problems, examples rather, then you'll understand, okay? So my claim is that these two guys can be written in this form. What did I do? I have dq over dt, this guy here, dq over dt. Then you have di over dt. These two on the left hand side, dq over dt and di over dt. These are the two elements of this vector. This is vector, right? Vector meaning you have a, b. Your a is this, b is this. Okay. So then on the right hand side, then you have, this is your matrix A. I call it A. And this is your vector X. So what is the difference between X and X dot? This can be X dot, because this can be written as Q dot. This can be written as I dot. What is dot? Dot meaning derivative with respect to time. Okay, this guy is derivative with respect to time. That's why I can simply write Q dot. This is with respect to time also, I dot. I then dot, right? You have double dot here. One for I, the other one for time derivative. So I dot dot. Sorry, I dot. Sorry. So this is your X. If this is your X, can I call this X dot? Are you okay with that or not really? Then this is your V, this is your U. Okay, so X dot equals A times X BU. That's my claim. But the thing is how, right? How did I claim that? Let me show you how I claim that. Do the matrix multiplication. So when you do that, so what do you get? How do you multiply this together? How do you multiply these two guys? So your first is dq over dt. Let me talk about the first one, okay? The top one. So dq over dt equals, this equal, then what is this here? What do you, if you multiply, what do you get on the top? Multiply this guy with this guy, right? What do you get? 0 times q, 0 times q, then plus 1 times I. So then here, what do you get here? 0 times bt. So let me simplify this guy. dq over dt equals, this is I, right? I. Look at that. This guy exactly matches with this guy here. So the top one makes sense, right? Top one makes sense. Now let's do the bottom one, whether the bottom one does make sense too. So bottom one is this. What is the bottom one? Bottom one is you have di over dt. So this guy, di over dt, then equal. So what do you multiply here? When you multiply these two, what do you get? Negative I over LC. Oops, negative 1 over LC, not I. Negative 1 over LC times Q minus negative, help me here guys, I'm lost. Does it make sense? Then what do you have here? Plus 1 over LVT. So is this equal? Are the same? Is this guy equal to this? di over dt. What is this guy? Q, negative Q over LC. This guy. Then negative RI over L. This guy. Then V over L. This guy. So my claim is I can write these two equations as this. That's what I verified now. I proved my claim. Now I'm ready to answer a question. So you need to figure out, once you see, the thing is, once you see this, you have to be able to figure out your A, B, X dot, X, and U. Okay? So you have to be able to figure out these guys from this equation. Okay? My suggestion is just write equation like this and go back and do the multiplication. Okay? If that doesn't make sense, then make the modification here, somewhere, wherever you want. So far, so good. Now our output equation. Now let's do the output. What is your output? Output is across the inductor, right? Let me see here. This is my output. Output is the voltage across the inductor. So let's figure that out now. So output equation can be written in this form again, where Y is a vector, C is a matrix, X is a vector. It's the same vector, right? What is X? We already have this X here. This X is same X. C and D, they are different matrices now. Okay? And Y is another vector. So you can write your Y in terms of this. And that kind of equation is called output equation. So we have, now we talked about two equations. One, the state equations. This is state equation, right? This is state and this is output. Okay. So combination of state and output is called state space representation. That's the thing. So once we have both of this, we are done. So we are done with state. Now let's do the output, then we are done. So can I write my output equation like this? So what is your y? Y is BL, right? It's given in the problem. This is your y. Now, how do you figure out your C? How do you figure out the C there? How do you do the BL? Let me go back to the picture here. So how do you do the, let's do the equation again. So what is the loop equation again? Let me write the loop equation. So I call it BR, I call it BL, I call it BC, this is BT, right? If you go from here, your BT is positive minus BR, then BL, then BC equals 0, right? That's the thing. So then what is your what is your BL from here? Help me. BL is BT minus BR minus BC, right? What is your BT? We don't know. That's the source, right? What is your BR? Help me here. Guys, you need to help me, please. I'm lost. Can I call it I times R, Ohm's law? What is my BC? Q over C. That's my BL. This is what I'm writing in the next page. Let me show you here, right here. See, this is my BT, this is my RI, this is my Q over T. That's what I wrote. Can I rewrite this guy as this? That's what I'm trying to see. So what is your Y? Y is BL. If I choose my C like this is my C vector. C vector has -1 over C and negative R. Then D is 1. If I choose like that, can I get this? Let me see. So your Y is BLT equals, what is your C? -1 over C, negative R. Then what is your X? X is QI. Then what is your D? Your D is 1. Then what is your U? U is VT, right? I simply cannot write VT here. Let me simply write VT. So let's multiply this guy. So BLT equals, what do you get here if you multiply these two? This multiply with that, minus Q over I. This multiply with that, minus IR plus BT. So look at that. So this is exactly same. Meaning this is my C. This guy is my C. This guy is X. And this is my U. So this is my Y. Your output equation can be written as Y equals CX plus U. That's what I proved.
Wait, what happened to the D?
Oh, D is 1.
Oh, okay.
If you just put it 1, right? D is 1.
Oh, I see. Sorry.
That's okay. That's okay. Now, I promised you a couple of things before. Now I'm going to do that. So I talked about energy storage element, right? So what is energy storage element? I'll talk about that. And what is energy dissipator element? I'll talk about that. But before I go there, I want to conclude something on this one here. So you have this equation and you have output equation, right? You have output equation. So what are these called? What is the name of the x? This x is called, state vector. This is the same x, right? This is called state vector. What is your x dot? X dot is derivative of the state vector with respect to time. That's the name. We are naming them now. What is y? This y is called output vector. What is your u? This u and this u. These two are called input or control vector. These are called, sometimes we call it input, sometimes we call it control. What is A? This A. The name of this A is called system matrix. When I say system matrix, you should quickly keep in your mind, okay, this is this A. Not this guy, not this guy, not D, not C, not B, this guy right in front of X, okay? When I say system matrix, you have to keep that in mind now. Okay, I'm talking A, okay? It is B. What is the name to B, given to B? The name of this B is input matrix. And what is the name of this C? This C. The name of this C is output matrix. Then what is the name of this D here? This D. The name of this guy is feed forward matrix. These are the names, okay? Having said that, let's talk about, after that, let's talk about the energy storage element. Remember we talked about energy storage element and energy in the previous slide. I introduced energy storage element. So we talked about electrical system. In the electrical system, what are the components? And also in the translation system, right? Remember chapter 2? What are the components here? Electrical, you have a spring. You have capacitor, mass. Then you have viscous damper, right? You have those elements there. How was in translation? Oops, I switched it, didn't I? I did. My bad. This is translation. This is electrical, right? In the electrical, so what is the thing that is equivalent to spring? What did I do? Spring is capacitor. Yeah, that's okay. Capacitor. What is the equivalent of mass? Inductor. So what do I mean by that? The inductor in electrical system plays exactly the same role that the mass plays in translation system. That's what I'm trying to say. The capacitor in electrical system plays exactly the same role as the spring does in translation motion. That's what I'm trying to say. Similarly, viscous damper in translation motion plays exactly the same role as the resistor does in the electrical system. Now, this spring, mass, capacitor, and inductor, they are called energy storage element, while the resistor and viscous damper, they are called energy dissipator elements. Does it make sense?
Wait, doesn't the spring and resistor are kind of the same?
No.
No?
No. They look like same when you make them, right? This is spring. This is resistor. But practically, what if you talk about the working principle, they're different. So spring, it stores energy, right? What is the energy stored by spring? 1/2 kx square, right? It stores energy. Similarly, capacitor also 1/2 qv square, right? That's the energy stored by the capacitor.
Okay, I see.
Okay, so the similarly inductor and mass also store the energy. What is the energy stored by mass? mgh. So, but the resistor, it dissipate energy. Dissipate energy. You can verify that because if you suppose you have the circuit, right? This is connected to the battery. Then after some time, what happens? This becomes hot. Why? Because this guy dissipate energy. Similarly, viscous damper, it dissipate energy. So these two components are energy dissipator, and these four components are energy storage element. Make sense? Yes, no, maybe?
Makes sense to me.
Okay, very good. Now last time what is the method we used last time? What we did last time was method 1. I call it method 1. What we did is we had second order differential equation. Then we changed into 2 first order differential equation, right? That's the approach we did. Now next method is, I call method 2. In this method, what I do is I count the number of independent energy storage elements in the system. So this is what method 2 is all about. Okay, we count them and do something else with the, once you figure out the energy storage elements in the system, then you do something else. Okay, so that's what we are going to talk about. So first, your first goal is to count the number of energy storage elements. So suppose you found 2 of them, 2 energy storage element, then you must have 2 state variables. Suppose you count and you found 3 energy storage elements, then your system must have at least 3 state variables. Otherwise, you cannot describe your system completely. Okay. Step 1, write the simple derivative equation for each energy storage element. For each energy storage element, you can write derivative equation, the equation that involves derivative in it. Step 2, you select each differentiated variable as state variable. Each differentiated variable. Suppose you have dq/dt equals I. Then that differentiated variable, this guy, differentiated variable is a state variable. Then we express all other system variables in the equations in terms of state variables and input. Suppose, see what I meant. So let me say what does that mean? So suppose you have dx1 equals dt equals, I don't know, p. Okay, but you have state, what are the state variables? State variables are, let's say, x1 and x2, and your input is, let's say, v, right? Let's say input is v, but you have the system variable p here. Now you have to write this p in terms of x1, x2, and v. That's what I'm trying to say. So then we express all other system variables, in this case p, could be q, right? Could be p and q, in the equations in terms of state variables and input. State variables and input. You have to express this guy in terms of these 2 guys. So these 2 are state variables. This is the input. Okay. This gives you, what does this give you? This gives you state equation. This is step 2 gives you state equation. Now, what else do you need? Besides state equation, you also need output equation, right? Output. This step 3 gives you output equation. So it means write the output variables as linear combinations of state variables and input again. Suppose your output equation is, let's say, output variable is, let's say, I don't know, m, right? So then you have to write this m in terms of v and also x1 and x2. Sometimes you might not be able to write in terms of everything, right? Sometimes you might miss x1, sometimes you might miss x2, sometimes you might miss v, sometimes you might miss x1 and v1, but you try to, you know, as much as possible, you try to get this m in terms of all those things. If it is missing, means that coefficient is 0, right? Remember, we had dx1 over dt equals coefficient x, I don't know, a1, x1, I don't know, x1, I don't know, x11, a11, I think a11, we had a11, I don't know, a11 x1, a12 x2 plus, you know, that kind of thing, right? If something is missing, means your a12 is 0 or a11 is 0. It could be like that, okay? But you try to write in terms of x1, x2, and the, what is the other one? Input, right? Okay, let's use that rule here. Let's solve this problem by using that concept here. So find, what is our concept? What is the goal? First step is to find the number of help me here, energy storage element. What are the energy storage element in this circuit here? I need your help, please. What are they? You have the inductor, and the resistor is not in energy storage. You have the capacitor. So how do you write differential equation in terms of L and in terms of C? What do you know about this guy? Is there any way that we can write differential equation about this guy, involving this guy? A differential equation that involves L. Help me here to figure that out. What is the voltage across this guy? VL. How do you write VL? L DIL over dt. See, we found L, and it involves difference, you know, derivative equation here. You have the derivative associated with L. So one of the equation will be this guy. So we found one derivative equation for L. Derivative equation for L. This is for L. Now, similarly, can you find the derivative equation for C also? You have to have derivative equation, okay? Otherwise, it doesn't work. You have to have derivative equation for this guy. What kind of equation do you think you can write in terms of C? In terms of C, but derivative. IC, again, this is your physics 112. IC equals C times dVc over dt. That's your derivative equation, including which involves C in it. It involves C and there is derivative. See, this d by dt. This is derivative equation and involves C. That's what it is. This is your first step. So far, so good. Do you follow me? Please. Please say no, make me happy. I don't mind. I have to say something that makes me happy.
Okay, can I just ask where, I don't know, where do you get like the I sub c equals c times dv c dt?
Let me, so I have to take you back to physics 112 now, okay?
Yeah, this is a consequence of me not having taken it for many years, so sorry.
Yeah, that's okay, that's okay. I'm here to help. Only thing is that you need to ask questions, that's all. Otherwise, I don't know what the confusion is, right? So that's the thing. All right, so this guy comes from here. So do you remember this guy here? BC, B equals Q by C. Because what is the capacitance of a capacitor? Q over B, that's the definition of capacitance. So this can be rewritten as this. Okay.
Yeah, I see that.
So what do you have? If you take the derivative on both sides, what do you get? Take the derivative on both sides. dB over dt equals 1 over C dq over dt, right? Take the derivative on both sides. So then what do you get from here? What is your dq over dt? I. So it means dB derivative of B. I should have said derivative of B instead of saying dV over dt. So 1 over Ci. So what does this give you? What is your I? I equals C times dV over dt. There. That's the thing, right? Does it make sense now?
Yeah, it does. Thank you very much. I
You're
appreciate
welcome.
it.
You are very welcome. So we did the part one, step one rather, okay? Step one is done. So find the derivative equation for each energy storage element. These guys done. Part one is done. Now step one is done. Step two. What is step two if you remember correctly? What is step two? So express all the other variables. So now find out the state variables. What are the state variables here? Guys, help me here. What are the state variables here? Guys, I need your help. I cannot do anything without your help here.
I and Q.
So a differentiated variable are state variable. Keep that in mind. Differentiated variables is very easy to figure out. R is that simple. What are differentiated variables here?
Would it be VC and IL?
Exactly. These guys are differentiated, right? Yes, these two guys are state variables now. See how easy it is? Done. Keep this in mind. Differentiated variables are state variables. Boom. It's that easy. So our state variables are BC and IL. Now we know these are state variables and anything else is not state variable, right? Because you don't need more than two state variables. Why? Because you have two energy storage elements. So your equation is second order, meaning you don't need more than two. Okay, so that's why you already found them. BC and IL are state variables. These are not. These are not state variables now. The thing is, these are called other system variables. So BC and BL, sorry, BC and IL are state variables. IC and VL are called other system variables. Okay. Now your goal is to write those guys as a linear combination of state variables and input. Now this should be written in terms of IC. This is what I'm saying. IC and VL has to be written in terms of BC, IL, and VT. These two are what? State variables. This guy is input. You should be able to write your state variable. Oops. What did I say? Yeah. So these equate these. I need more sleep. Okay, guys, wake me up, please. So IC and VL are the other system variables. They should be written in terms of state variable and the input. That's our goal. How can you do that? How do you write IC? Let's begin with IC. How do you write IC in terms of BC, IL, and BT? Then we'll talk about BL. Okay, how do you write IC in terms of these three guys? Okay, let's IC, right? IC. So IC and what the other one?
VL.
IC and BC. Huh? Yeah, BL, sorry. Yeah, thank you. Yeah, thank you. Yeah, my bad. So IC, right? You are talking about current. What kind of rule do you want to use? Current. What is the rule for the current? Do you remember any rule for current? If you want to find current, Kirchhoff's voltage. Help me here. Kirchhoff's current law, right? Kirchhoff's current law. So let's use that Kirchhoff's current law to figure out your IC. So what do you want to so let's say this is the node you want to consider. At this node, what is the Kirchhoff's current law? Help me here. IL. So this is the ingoing, right? Incoming, not ingoing. Incoming is considered to be minus outgoing. What are outgoing? IC and IR, they are outgoing. They are considered to be plus. They should be equal to 0. Then what is your IC from here? What is your IC from here? IC equals, guys help me please. Negative IR plus IL. That's what it is. But our goal is to write IC in terms of BC and IL. IL is good. Look, we found IL. So how do you convert this guy to BC now? Did you get the idea? So this guy has to be converted. How do you convert this to VC? So what is the relationship between IR and VC? Help me, please.
What was that? The difference between VC and IR?
No. How do you write? Because your goal is what? Your goal is to write IC in terms of BC, IL, and BT. BC, IL, and BT. You have to write your IC in terms of BC, IL, and BT. So we found this equation, there is no doubt. Even though we found it, we haven't finished our task yet because your IC is in terms of IL, this guy is good. In terms of IL, but you need to find in terms of BC also. And if you can, in terms of BT also. So how do you do that? IL is there, good. How do you change your IR, this IR, in terms of BC? Is there any way to do that? BC, right? This is what your BC. This is your BC here. This is your BC, right? So this BC equal to this thing. Can I say the voltage difference between these guys BC? Can I say it? Then can I say your I equals BC over R? This guy. Ohm's law. BC over R is I. That's what I did here. See, I changed my IR to BC over R. Look at that. It means my IC is in terms of BC and IL. My IC is in terms of BC and IL. But I couldn't find in terms of VT. That's okay. You cannot do that all the time. Okay, so far so good. Please. Can anybody help me here? So far so good. Not really. I request you guys, please. Help me here. Any question?
So you're saying that basically you're substituting IR, you're able to substitute IR with VC over R because the current, or I don't know, because those, like, basically the voltage drop over that area is the same for both of those elements?
Yeah, because they're in parallel, right?
Yeah, okay.
So R and C, they're in parallel.
Yeah,
That's
all
why-
right.
Yeah. So far so good. This one is good, right? Now how about the other one? Now I have to do BL. Now I have to do BL in terms of BC, IL, and BT. I have to do that now. So how do I do that? I'm almost done, okay? Just give me 1 minute now, that's all. So what is your, how do you write your, you need to do what? BL, right? Okay, BL meaning you need to talk about this mesh now, because this mesh contains BL, right? So in this mesh, how do you write the Kirchhoff's voltage law? BT, BL, and VR, right? Equals 0. So what is the thing? Sign. Here to here you go positive. This is positive. And here to here you go down. This is negative. And here to here you go down. It's negative. So what is your BL? BL equals BT minus VR. Does it make sense? Or you made, I made a mistake?
I know you just said you made a mistake, but like I see that eventually it gets to minus VC plus VT. Can you replace the VR with the VC because of the thing in parallel again?
Yes, that's what I'm
Yeah.
talking about. Yeah, thank you. So BR is replaced by now BC, because our goal is to write BL in terms of BC, IL, and VT. So I'm done. So I wrote in terms of BT and BC. See? I have it. Now I have to go to the step 3 now. So maybe I just stop it here for today.
Okay. Take care, Professor.
All right, thank you guys. Thank you so much.